So you are saying that what was that there is no answer for this one. Do you need answers for this? Is not enough? It's fairly similar to this one, isn't it? Okay, I'll see what I can do for this. Okay, I'll try to do some of those and send put it there. Is that only for 4 tutorial 6? Okay. Have you done all of those? Okay. Anyway, I'll probably try to give some answers for that. Okay, so we'll make a start. And today what I'm going to do is, if you remember last week, if you attended the class, we are looking at bending stresses. And I sort of, or rather we derived the formula for bending stresses. And that it's related to bending stresses with moment with this formula, sigma over y equal to E over R is m over I. And we did an example. And one of the quantity related with this problem came up is with the cross-sectional property called I, or second moment of area. And we said that for a rectangular section is BH cube over 12. So if it is for this rectangular section about axis 1, 1, B is 30 and height is 80. But if you do carry out the second moment of area about axis 2, 2, which is the vertical axis, then of course you need to rotate that way. So B would be now 80 and height would be 30. So you have to see which way the beam is bending, about which axis, and then take appropriate I, because it could be different values if those width and heights are different. So I'll spend some time today or the second moment of area and how to calculate that, what is it, and how to do it for other cross sections a little bit. So this I, or the second moment of area, would come quite often in your studies, and this is one of the very basics one, and it will come in hydraulics or fluid mechanics, whatever you are doing in your first year for civil or aerospace students. And then this quantity will come, and then again in the following year, whatever you do, this second moment of area will prop up in various other units. So I'll spend today on the second moment of area in the morning. The lecture notes is the last 2 pages of the, so it is part 7 related to second moment of area. So it's uploaded in Blackboard, I think, for this week's content. For this week's content, if you go, it's uploaded there. So part 7 is this part which I am going through at the moment. So this is what we are doing. Okay, so what is second moment of area? So we'll ask the question. So before that, let me take a couple of step back and then start getting into second moment of area slowly. So if you have a cross section of a beam, let's say a beam is something like this, and you have got a cross section. So if you have got a beam and you have got a cross section like that, okay, so it's a rectangular cross section. Now if you are given this rectangular cross section, where do you think its centroid will be? How do you find the centroid? Go on. Very good. So this rectangle has got so-called axis of symmetry. So according to you, if I do a vertical symmetric axis and if I do horizontal symmetric axis, then centroid, if I show it to by this point, then it would be there. Centroid would be there at that point. So if I take that approach, if I have got a circular section, what do you think centroid would be? So I take your answer again and I'll do two axes of symmetry. So centroid would be at this point. So can I say, take this approach and say, okay, I have got an equilateral or a triangle of some form. Let's say it is equilateral triangle. So if it is equilateral triangle, so A, and A, then of course I can use the symmetric axis, and then also I could see if it is equilateral, there would be another symmetric axis over through this way. So my centroid would be here. Okay? So what is centroid physically? I mean, how do we find centroid? What is centroid? Go on. Yeah, but sometimes that is true so far where they have got axis of symmetry more than one, right? But what happens if I give you a cross section which does not have any axis of symmetry, let's say, or maybe have got only one axis of symmetry, or may not have any, for example, an unequal angle section. Doesn't have any axis of symmetry. So what is centroid? Center of mass? What is center of mass? Where the whole weight can be concentrated. It can be balanced on that point. All true. So balance about what? Balance about the point. So that idea actually is quite a powerful one. So one way you can find the centroid is you can cut out a shape of this one, say rectangle, and then you think, okay, you hang that piece with a piece of thread, for example, and then of course due to the weight it will hang. Say for example, if you tie it up along this, if you take this rectangle and if you put a string attached to the corner, then it will probably hang in this way, vertically down, probably that way. So its centroid would be along that line somewhere. Okay? Then you attach to it another point and hang that way. And then if you extend your thread, for example, so this is your thread, and then you extend that, and then you again draw it, put it into another corner, attach it with a thread, for example, then it will be in this way, and put it probably through the middle somewhere, attach a thread and hold it in this way. And then if you draw those lines, then that would give you, on the piece of paper that you had, then that would give you the axis of symmetry. So the idea is very simple. So you cut out a shape from a piece of paper or a material, you put it on to stick a glue and a string at one point and hang it. So once you hang it, then you'll see, then you continue the vertical line through it. So you draw a line and then you attach to another point you attach to another point, if you then see that they will probably meet at a point somewhere on the cross section or not. For example, if you do this case, where do you think center of centroid would be? In this case, if you hang this one, you probably find those lines will not meet within the cross section. It would probably be somewhere here. So outside the cross section, it is possible to have centroid outside the cross section. So that again your second point. So mass is apparently, or the whole area you can assume is concentrated on that point, and also it balances out. Somebody said that balances out the cross section on the other part. Now, if the cross section has got an obvious axis of symmetry, then we can easily determine this point. But it is slightly difficult to find out what the centroid of this type of cross sections are. So how do we find the centroid of the cross sections analytically? So that's the first thing which gives rise to this quantity called first moment of area. That gives you the idea of the centroid. So centroid we can find by so-called first moment of area. First moment of area. So that gives rise to the idea of the centroid. Now, what is the second moment of area that we are going to talk today? Second moment of area comes from, the term comes from, or the idea comes from, even some book will call it the second moment of area. If you pick up Structures book, some of them will also call it moment of inertia. Now, moment of inertia is strictly speaking related with a mass, not an area. So we are not going to use that term at all. So what is moment of inertia? Moment of inertia is, say if you have a string attached to a point, for example, and so you have got a string and you have got a mass attached to this at an end, and then you start to rotate that mass about that string. So the moment of inertia is related to the mass that you are rotating and the distance of this string, or the length of the string. So the moment of inertia, sometimes it's called I, sometimes it's called J, is equal to m times r square. So the moment times the radius square, which you have probably done in your physics at A level, or mechanics if you have done. So that is moment of inertia of a mass. So this is moment of inertia. The same concept, so it is related to with rotations. So similarly, when a cross-section rotation is in picture, so when a cross-section is rotated, so that could happen in bending, for example. That could happen in bending. So when you bend, cross-section rotates. Then this second moment of area comes into picture, and we call it area rather than mass. So moment of inertia, and instead of moment of area, we call it second moment of area. So what is second moment of area? So you have got an area, and then maybe some part of that area, and about some axis second moment. That means the distance of that area square, same as r square. So if this area is, small area is, let's say dA, and from this axis is distance is y, then we are talking about second moment of area is the area which is substitute for the mass times the distance square, which is same as the radius square. So this quantity is the second moment of area about that axis. So if this axis is the axis of bending, so it's related to this axis, to this idea of the rotation, second moment of area. And it will come into various other subjects that you do. So as we are going to do through it, so I'll probably go, do you know how to calculate the location of centroid using first moment of area? Do you know how to calculate centroid of a cross section? So if I give you a cross section like this, can you find out its centroid? Yes? Okay. Okay, so that I can tell, but I'm just asking if anybody knows. Yeah, because if there is no line of symmetry, how do you do? Yeah, okay. Okay. That is probably you can do. So if you know the centroid of the known area, then you can use that way. Yes, absolutely. So probably what I can do is, if you are not very sure, I can show you going back to basics, maybe showing by calculus, maybe. Okay. So let's say you have got a cross section. You have got a cross section which is B times H, and some people call it a rectangle. Okay? And you have to find the centroid of this rectangle. You have no idea what it is or where it is. You don't know. And you are not going to going to do any experiment or anything here. So you are not going to draw the line of action of the force, etc. So you want to find the centroid of this cross section. How do you do? So put that section onto an axis system. Let's say I take, this is my origin, and I take, this is the x-axis, and this is an y-axis, because I could see these two are 90 degree, and that is probably given. This is 90 degree. How can I find the centroid of this rectangle? Now, this is a big area. I don't know how the centroid would be. Now, I can go back to calculus, because calculus often helps us, and say, pick up a very small area within here. Maybe somewhat here. Very small area. And I know this area, let's say this distance is dx. So this one, if I draw a little bit bigger, let's say this is dx and that is dy. And that is at a distance x from this side and at a distance y from this side. So I know its centroid is from this. So it's in the sort of a, and this cross section, it's so small, I can make dx and dy as small as I like. So I'll make it so that there is probably, it's not very much bigger than a point. Of course, strictly speaking, it has to be, but very little area. So where I can find the midpoint, and I'll say, okay, this is my centroid at that point. So I know this is the centroid for this little section. This is my centroid at this little section. So what would be the centroid for the whole cross section? Now then the idea of the moment comes. So if the centroid of the whole section is somewhat here, for example, let's say somewhat here, that's some arbitrary point in here, and let's say the distances along the x-axis, let's say I call it, this centroidal distance is, say, x bar or something, and the distances of that from my origin is y bar. So that's the distance for the whole centroid for this rectangle. Let's say that's my main aim I want to find out. So this first moment of area gives me, if I calculate this location of centroid, how does it give? So if I know the area of this cross section, total area is equal to, for this big cross section is B times H, or this total area. Or I can find out some other way, or I could say, okay, instead of big area, this is a big area A. So what we need to do is, I can take a moment of the big area about this point. So that would be So the moment of this big area would be A times x bar. That is a big area times x bar. Okay, so that's the moment of the whole area about this axis, A times x bar. So the area, which is, so you can think about the area here as a some form of weight, some form of force, but it's, so you can say, okay, the whole area, moment from the first line, from this line is A times x bar. That should be equal to sum up of all these little areas that make up this cross section. So that must be equal to dA times x, because that's a small area. Now it's a sum of all of those. So if you integrate that. So we know dx is dx times dy. So x times, so you could say dx times dy. So you could then carry out the integrations over dx and dy. So if you do two integrations in these cases, so x would vary from 0 to b, and y would vary from 0 to h. Okay. So that's the area in this case. So if I do this integration, carry out this integration, x and y are independent to each other, 90 degree. So I could separate out those two. So I could say x times dx and times dy. X varies from 0 to b and y varies from 0 to h. So what would be the integrations? X dx would give me x square over 2, and that would be from 0 to b. And y would be, in dy integration is y, that would be from 0 to h. So this would be b square over 2 minus 0 times h. So that is b square times h over 2. And that is equal to A times x bar. Now A, area of the whole cross section, let's say you have managed somehow and find the cross sectional area. And we know A is equal to B times H. So B times H times x bar. So this will give you x bar is equal to H over 2. So B over 2. So that means it is half along that direction. Now if you similarly continue for y and write down another equation, say A times y bar is equal to integrations of dA times y, for example, the moment in this direction. This will ultimately will give you y bar will be equal to h over 2. So this quantity is called first moment. So the moment of the area, that's why it is called first moment. Just to differentiate between the second moment means you make that as a square. That's the whole idea. So you can use this same principle for any other cross section that you do. So for a rectangle, we can find, okay, from a corner, if you go half the width and half the height up, that's where your centroid will be. And then this idea of dividing the cross section into some known parts is what you have been saying, that how do we do second moment of CG of this cross section. You could say, okay, I could say it is made up of two rectangles, rectangle number 1 and rectangle number 2. And then you start from a point and then find out where the CG would be. Okay. So that is the way to do that. Now, are you confident how to do in this case now? Yes or no? No. Okay, doesn't look like. Okay, so are you okay in here? How do we calculate this? Yeah. So the way to calculate CG using first moment of area. Now, if I have a cross section which is slightly non-standard in a way that there is no obvious symmetry, then let's say this is a cross section. And let me give some dimension. Let's say this is 100 millimeter, and let's say this is 10, And let me make my life a little bit easy. Let's say this height is 160. 160, so that this is also 10. That's it. So 10 millimeter, all of that. So I want to find the centroid of this cross section. Now, again, as before, I will draw an axis system. So let's say my axis origin is here, and I'll draw x-axis along that way, y-axis along that way. You could put it in any other points, that is fine. But makes it easier if you do it at a corner, as you know. But it could be any other point, this centroid. This origin could be, it could be here, it could be here, anywhere. And let's say the centroid is somewhere here. So this is the CG. And this centroid is at a distance, let's say x bar from the origin, and at a distance y bar from this origin. So the coordinate of this centroid, if I call it C, so coordinate of this centroid is x bar, y bar. Let's say that's the centroid. So how do I calculate that? Again, I will use the principles that we have just said. I'll divide it into two parts. So rectangle number 1 and rectangle number 2. So rectangle number 1 has got a dimension of 150 by 10. 150 by 10, and I know its centroid would be from my this calculations before, that it is halfway up as well. So I know its centroid would be at a distance halfway up. Say here is the centroid. So I know that's the centroid. Similarly, rectangle number 2 will be, rectangle number 2 is 100 by 10. So this way 100 and that way 10. And its centroid would be in the middle. So how much is the distance from this origin of this centroid? So from the origin, its centroid would be at a distance of half of 150, which is 75, and plus 10. So this distance is 85. This distance is 85. Because it is 75 from the top, because 150 is the distance, and then 85 because 10 would be from this side, and this one would be 5 from the bottom. So how do I calculate the CG of the total section? So the total area say A will be, or rather if I put area of A1 is 1500 millimeter square. That's for part A. For part B it is 1000 millimeter square. That is A2. So the total area is A1 plus A2. So that would be in my case 2500 millimeter square. So to find the centroid for the whole section, I'll say area exactly the same way as I have done before. A times y bar, that is the vertical distance, A times y bar will be equal to the constituent part's first moment. So the constituent part is 2 in this case. So instead of integration sign, because here it was very small distances all over the area, here we have got only 2 things because we know these 2 things how to calculate. So for the first area is 1500 times its distance from my origin. Now one thing you have to do is you have to calculate the distance from the same axis. So A times y bar, which is this distance, so the total area would be the first area 1500 times 85. That's the vertical bit. plus the second area is 1000 times it is at a distance 5 millimeter from this x-axis. So you know A, so this will give you what is y bar. So if I do these calculations, you will get times 85 plus divided by 2500. So that gives me 53 millimeter. So that is 53 millimeter is this distance. Now if you want to calculate what would be the horizontal distance, then you could say, okay, I'll use the same principle, A times x bar, which is the horizontal distance, would be my first area, which is 1500. 1500 x bar is from this axis is only 5 millimeter. So that is times 5. Plus the second area, the area is 1000. And how far it is from this point? Halfway up, so which is 50 millimeter. So that's the idea. So A is the total, as you know. So that will give me x bar. So the x bar then I could get is so x bar I'll get 23 millimeter. So that gives us the idea of the locations. So which you could see is outside the cross-sectional area. So this idea of multiplying the area with the distance is called first moment. And the first moment gives you the idea of the centroid. Second moment of area, as I said before, is related with rotations. So we need to show how to calculate the second moment of area now. Now is this clear so far? Yeah. So you could do it for the same principle using for other cross sections how to calculate the centroid. If there is an obvious axis of symmetry, so the centroid will lie along that line. If you can find another axis of symmetry, then draw those two axes of symmetry, and wherever they meet, that's where your centroid is. But when the axis of symmetry is not obvious or doesn't have any axis of symmetry, then you need to apply this analytical way to find out where the centroid could be. Okay. Now going to the second moment of area is related to the rotation. So instead of multiplying with the distance, we'll multiply with y square. Okay. And I'll go back to calculus again, and we'll find out this second moment of area, how to calculate that. Okay. Is that okay? Okay. So second moment of area comes from axis of rotations. So I'll use again this rectangular cross section of dimensions B and H. B and H is the dimension, and it is the axis of rotation that is important here. So you could calculate the second moment of area about any axis system. So you could have x and y from the centroid. You know centroid would be here in the middle. You could calculate centroid from this point as well. Or what you could do is you could calculate from another point. So I'll show you both how to calculate and what is the way to do that. Now let's say I'll calculate about the centroidal axis first. So this is my axis, and I call this axis 1, 1. So I'll calculate centroid of area. And this is in a way taken through the center so that the top half is h over 2 and bottom half is also h over 2. So that's going through the middle. So what is the second moment of area of this cross section? So what we need to do is, again going by calculus, I'll use a small area somewhere here, or as we are calculating about this point, so what we could do is we could take a strip as well, Or if you say, okay, I don't know how to do the strip, then you could do the same way as dx times dy as well. So all of these would give you the same answer. Now let's take a strip somewhere here. Very small strip, width b, and the thickness is, as I am doing in the upward direction, so let's say that is dy. And it is at a distance y from this axis. So b times dy. So second moment of area of this strip, second moment of area of the infinitesimal strip about axis 1, 1 will be the area, which is area of this strip, which is b times dy, so that's the area, times the distance square. So that is its second moment of area of this little strip. So the area times y square, as opposed to the distance times area times distance. So, and why this is square? As I said, this comes from the idea of the rotations. So it's the m times r square, as similar to this. So it comes from b times y square. Now why this square? Now of course why the second moment? Now that's again, the force in this case is proportional to m times r, and then the moment or inertia is another r in this case. So exactly the same way, so the area times would be related with the force and then taking into the square. So that's the second moment of area. So second moment of area for the whole section would be, so the second moment of area for the whole section would be integrations of that. So second moment of area of the whole section about axis 1, 1 would be integration, if I call it I is the symbol, is the integrations of b times dy times y square. Now only variable is here dy, so y would vary from minus h over 2, because this is the positive y, if we take this is the negative y, minus h over 2 to plus h over 2. Now b is constant, so that can come out of the integration sign, and that would be y squared times dy minus h over 2 to plus h over 2. So if you do integration of this is y cube over 3 and minus h over 2 to plus h over 2. So if you complete that, it will be h cube over 8 times 3, 24, minus h cube over 24, so that will give you b h cube over 12. So that's the second moment of area of this rectangle about an axis 1, 1. Now sometimes it would be also useful to find out second moment of area about another axis, which is possibly parallel to that one. So like in this case, if you have got a composite section, if you have got to find out second moment of area of this whole section, so through the centroid, so not the centroid, the axis would go through the both rectangle centroid. What do you do that? Then there is this idea of parallel axis theorem, which says that you can calculate the second moment of area about any other axis. Let's say I've got this rectangle. I now want to find out the second moment of area about this axis, 2, 2. So this theorem says that I22 will be I about its centroidal axis, I about the centroidal axis, plus the area of the cross section times the distance between the two axes square. So distance between the two axes square. So I about 2, 2 for this example would be I about the centroid, we know bh cube over 12, plus area of the cross section is b times h, distance between them is h over 2 square. So that would be bh cube over 4. So if you add them in, that would be bh cube over 3. So this is sometimes useful, and this is called parallel axis theorem for second moment of area. And we show that to you here, parallel axis theorem in the notes. So you could see that how it is done and what it is by reading the notes, and you could see that it would be bd cube over 12. I'm using h here, and in the notes it's d, but that's simply as it is. So you can using these two expressions any second moment of area of this cross section. Often using the rectangle makes the sense, and you could use that, and you could get them in any data table or the chart. One thing you should remember is this rectangle case and the circular case. If you do these two, then you can find out of the lots of cross section. If it is an I section, if it is a T section, if it is a channel section, angle section, all these sort of things you can find out from a rectangular cross section. So the things that you need to remember is possibly these two. So one is, of course, the rectangle, which I will draw it again just for sake of that it goes in your head. So if you have got here, and I say two axes, and this time I'll name them A and B. So if you have got axis going through the middle, and where you have got the centroid there. So let's say this axis is A, and you have got a vertical axis, let's say B somewhere here. Let's say you have got a vertical axis B here, and this cross section is B and H is the dimension. So this dimension is small b, and this dimension is small h. Then I about AA, which is this horizontal axis, will be equal to b times h cube over 12. And I about the vertical axis would be, then you need to rotate that one. So instead of b now becomes h. So this is the axis of bending. So I about the BB axis would be, instead of B you will put H, instead of H you will put B. So that would be H B cube over 12. So that's the one thing you need to remember. So that is one rectangle case. And instead of looking at the data table, if this is in your head, and this one thing to remember, this formula means axis going through the centroid. That's the most important bit. So this is the centroid. If you want this about any other axis, you use the parallel axis theorem. So you find out what about its own centroidal axis, then area times the distance squared between those two axes. So this is one, I said. The second one I'd say you need to remember, because that one, if you don't have the data table, deriving that, of course you can derive it, would be probably not a trivial exercise. So if you've got a centroid here for a circular section. So if a circular section has got a diameter d, and as you know it's a symmetric axis about anything, so I could say centroidal axis CC in this case is pi d to the power 4 over 64. One thing to note that here the dimensions are to the power 4. So second moment of area will always have units of meter to the power 4, millimeter to the power 4, centimeter to the power 4, etc. So if you do not write the units, or not very sure about the units, please make sure you do, otherwise it will be deductions of marks. So these are the two basic cases that I ask you to remember. Now one of the things that you then need to do is use those principles to use the second moment of area of this I section. How do you do? Now again, you can think of this section is made up of three rectangles. One at the top, called top flange, one in the middle, the wave, and one in the bottom. Now you know second moment of area for each of these rectangles about its own centroidal axis. So use BD cube over BH cube over 12 or HB cube over 12 as appropriate, and then use the parallel axis theorem to convert that to about the middle of the axis. So that is one way. And the second way, for at least this case, you could clearly see that you could assume for this problem, you could say, okay, what about I need to find out centroid second moment of area about this axis. What will happen if I consider this is made up of two cross section. One is this big rectangle for which I can find the second moment of area, which is D, and this is B. So that would be B times D cube over 12. So that's the big rectangle. And then I take out these two sides, for example. So I then deduct these two bits, which is B minus T and D minus 2T cube. So that, but only one thing is that has to be both about the same axis. If not, so what I'm saying is, if you have to calculate second moment of area about this axis, then you cannot just deduct from the whole to this one, because what you are deducting, their axis is different than the composite axis. You could do for horizontal axis, because the horizontal axis is the same or remains the same for the big cross section, BD cube over 12, or the outer cross section, and the inner, which you are deducting, they also have the centroid axis at the same level. So you could use this simple subtraction in this case, but not if you are doing about the other axis. So in summary, what we call first moment of area gives us the idea of the centroid of the cross section. So you can use symmetric principles to get the idea, cross section centroid, but if not, you have to do analytically, then use this first moment approach to calculate centroid.
Can we find the second moment of area with respect to two different axes? Like, we find the first moment of area with respect to x-axis, and then find the second moment of area with respect to y. So the integral becomes x, y, dA.
It would be xy. Yeah. That is called product moment. That's a slightly different concept. I don't think I'll cover that, because that comes from something called, that is there. That is what is called unsymmetrical bending. So when the bending is not symmetric, so you put a load in the vertical direction and the beam doesn't, or whatever, the bending doesn't happen in the vertical plane. It happens on the vertical plane as well as the horizontal plane. That's called product moment of area, so which is x and y involved both. So good thing is that product moment of area is 0 about the axis of symmetry. So I don't think I'll go there, because that will confuse a lot. So you'll do it in the second year, product moment of area. Any other question? No? Okay, so the first moment of area gives you the idea of the centroid. The second moment of area is related with bending, and this is again with these 2 pages you need to know to find out how, but this is probably the summary that you need to remember and use it. So second moment of area of a rectangular cross section is BH cube over 12, where B is the dimension parallel to the axis. So B is this one, and if you are doing AA, that is BH cube over 12. Similarly, if you do second moment of area about this axis, now this axis means this is the axis, that's quite loud. This is the axis of bending, that would be HB cube over 12. And only other things that you need to remember is the circle. Okay, go on.
How do you know if the second moment area add or subtract? Say, for example 3.
Yeah.
The width is B
Yeah.
How do we subtract the t's again?
So if you consider this is two rectangle, then if you say that is total was b, so this length would be b minus t divided by 2. So and then this height would be d minus 2t. So that is the okay, that would be the height. So if you do for one of this rectangle, that would be b minus t over 2 times d minus 2t cube, and then the other angle again b minus t over 2. So if you can add those two together, that would be b minus t. Okay. Okay, so in terms of that, there is going to be a test this week, as you know, on bending moment, shear force. So go through tutorial sheets 3 and 4, please. I'll try to give you a couple of more solutions for tutorial 4, that number 2, but you must first attempt those. It will be mix of first test and second test. Some would be multiple and some would be calculations. Thank you. See you on Thursday.
I think I spoke to you on Thursday about doing, the roller coaster idea.
Yeah.
And I was going to ask, because obviously, the structure changes depending on where, the train is on the track.
Yeah.
So I was wondering how many sort of different points would you like us to analyse it?
The velocity, as long as you will do the worst case.
Okay.
So if it is in a loop, and I am assuming it's a circular loop.
Yeah.
So if you say, okay, it doesn't fall down when it is at the top, and maybe, I don't know, quarter points, or maybe at a 10 o'clock or something, or 10:30 or something.
Oh, okay. Yeah.
So about those, because that would be the main point,
stress.
isn't it? Yeah.
And then can we assume friction is negligible for our calculations?
You can, if you take that is the, and if you can give an indication that it could be altered the calculations if you do take into account friction in this case.
Oh, okay. Thank you very much.
Hi Ben.
Hi, Parker, how you doing?
Not bad.
For the bending moment and
Yeah. Yeah.
it's okay for us, because I watch YouTube videos also to understand more, but because the side conversation is actually different from the one we do.
If you are comfortable with any other sign convention, please be so there is sign convention is just for you to use one. So if there is no marks associated with sign convention.
So can I take
I have used it so that it is consistent across all the different chapters. If you do anything other than we are using in the class, you have to state that. And anyway, I also state that every time I do an example, that this is my sign convention.
The other side convention, I just say that
This is my sign convention. Yeah, absolutely.
Sir, I just wanted to ask, for the structural analysis,
Yeah.
can we use graphics and stuff like that? Can we use there? Can we do a structural analysis on them? As in,
Oh, you're for the coursework?
oh yeah.
Yeah, of course.
So, I mean, we could just skip the other question of the other question of the I-beam.
So, Dr. Rogers is going to start. So maybe